All right, everybody, welcome back. We're going to take a look at implicit differentiation in this lesson. So we'll see what that's all about. Okay. So to start, I got a couple warm-up problems here. Y squared equals 3x squared plus 5x, and y squared plus 4y equals 3x squared plus 5x. Define a couple of curves, and what we're going to do is we're going to find dy dx for these. Now, what looks a little bit different right away, hopefully you're saying it's y squared equals and not y equals. So how could we get around that here? Well, if we want to take the derivative of this, we probably want to try to get y by itself, so we might actually start by taking the square root of both sides. Okay, I'm going to ignore the plus or minus for now and just focus on the positive side here, which is fine. But now I can rewrite it with a exponent, and we have a quantity raised to a power, and we could use the chain rule to take the derivative of this at this point. So again, when we take the derivative of y with respect to x, we write that as dy over dx. That is the derivative of y. We're basically taking the derivative of both sides of the equation here. Okay. So I get dy dx on the left. On the right, we're going to use the chain rule. I got to bring down the power first, leaving the inside alone. Don't forget to subtract 1 from the power, then multiply by the derivative of the inner function. And we get this quantity back. If I want to clean it up a little bit, it looks like we're going to have a square root in the denominator, a 2 in the denominator, and then the 6x plus 5 up top. And that would be our derivative. Okay, we were able to get y by itself, then we're able to go ahead and move on from this. Okay, well, let's take a look at the other one. All right, it's kind of the same idea here. We have a y squared plus 4y equals, and we again want dy over dx. So we might be thinking try to get y by itself here, but give that a little bit of thought and see what you can do with that. Okay? To me, it's not quite as easy. I can certainly factor a y out if I wanted to. And then, like, if I wanted to get this y by itself, I could, I could divide by this, and then I'd have it over there. But I don't have y by itself in terms of x now. Okay, I want y on one side, just x is on the other. Right? We don't have that. We've got that y there. Okay, so there's different things algebraically we could do to try and get the letter y all by itself in just terms of x, but it's not easy. It's not easy to do, and in fact, there's going to be other cases where it's just darn impossible to do it. Okay. Well, that's where implicit differentiation comes into play. We're actually going to be able to take the derivatives of these things without having to get y by itself first, okay? So you're going to see sometimes you're going to have like powers of y and whatnot. Typically, we're looking at implicit differentiation, okay? So I call implicit differentiation basically the taking the derivative of one variable like y with respect to a different variable like x. Okay, anytime we take the derivative of one variable with respect to another, we're doing what's called implicit differentiation. In fact, we've done this year without knowing it was called that, because every time we take the derivative of y, what do we write? Like we did up here, dy dx. Okay, this is implicit differentiation. And the moral of the story is, if you're taking the derivative of y with respect to x, this is how you write that. Okay? Dy dx is the derivative of y with respect to variable x. So let's see, here's a quick example, and this is just y by itself. So again, to kind of reiterate what I'm saying is, when we're told to find dy dx, we want to see what is the derivative of y in terms of x going to look like, and we want this thing all by itself. Well, when we do something to an equation, we do it to both sides of the equation. So essentially what I'm doing is saying on the left, what is the derivative of y with respect to x? Well, we just write it like this. This is more or less your y prime. We've notated as dy dx. On the right-hand side, we're taking the derivative of this with respect to x. Using the power rule, we're going to get 6x, and actually I could write it times dx over dx. I took the derivative of an x variable with respect to x. Plus, if I use the power rule on 5x, the derivative is 5 times the derivative of x with respect to x. Okay, this is implicit. Now, let's talk about dx over dx. We haven't seen that before, and we're typically not going to write it. Well, what do you think that equals? What's anything divided by itself? 1. And so what we get back here, as you would probably imagine, is dy dx is 6x plus 5. But the moral of the story is this: when you take the derivative of a y term, you get dy dx. So let's take a look at this. This was back to our warm-up problem. We took the square root at the beginning to do it, but let's do it without now. So here's how it works. Basically, I'm going to take the derivative of this like it was an x squared. I'm going to bring down the 2, and I'm going to subtract 1 from the power, except it's 2y, not 2x, right? 2y to the first, then because it was a y term, I'm going to multiply by the derivative of y with respect to x, which is simply dy over dx. On the right, since we're taking the derivative of x stuff, it's business as usual. This would be 6x times dx over dx, if you want to write that, plus 5 times dx over dx. But again, if we're looking for dy dx, we're typically not going to write the dx over dx on that side of the equation. Okay, so again, it'll take a little bit of practice, but we're going to go through a bunch of examples together, and hopefully by the end it'll make some sense, all right? Now to get dy by itself here, by the way, we have to divide by 2y. And notice that this is how we get what our answer looks like here. Let's compare it to what we got up in the warm-up. Notice up here, we got 6x plus 5 over 2 times the square root of 3x squared plus 4x. And down below, when we just did it, we got 6x plus 5 over 2y, right? Well, believe it or not, these things are the same. If you notice, the only difference is what's in the denominators here, right? But what did we figure out y equaled at the beginning? Well, y itself is this square root. Okay, those are the same thing. So yes, this one in the top is just in terms of x, the one on the bottom is in terms of both x and y, but they are the same. Okay, and typically we leave it just in terms of y when we go through this process. Okay, so let's practice this a little bit. Here was that next warm-up problem that we really couldn't get y by itself too easily, but now we know we don't need to. So here goes, taking the derivative using the power rule. 2y to the first times dy dx, because it was a y term. Plus, the derivative of 4y would be 4 times dy dx. On the right-hand side, just 6x plus 5, because we already have x's over there. Here we want to get dy by itself. I notice it's in 2 terms, so what I can do is I can factor that out. And now if I divide by the quantity, we will have our rate of change, 6x plus 5 over 2y plus 4. And there's the derivative. Okay. And let's move on to the next one. Okay, and again, same instructions here, finding dy dx. Okay, the general derivative. So here we have some sort of weird curve. I don't even know what this would look like on graph paper. Okay, but it's given by x cubed plus 2xy minus y squared equals 10. And just knowing from experience on the AP exam, these are pretty common multiple choice types of questions. They kind of usually look like these. So let's go taking the derivative. So with implicit differentiation, we work from left to right. You might not have realized that, but we've been doing that since the beginning here. So the derivative of the first term is going to be 3x squared. Got to be careful on the second term. We have 2xy. Another way to say that is 2x times y. So what is that going to require us to use? Well, the product rule. Okay, you got to watch these products. We're multiplying variables. To take the derivative, we got to use the product rule. So derivative of the first piece, 2x, is just 2 times the other piece, y. Plus, I will keep the first piece, 2x, and I'll multiply by the derivative of y with respect to x, which is our first dy dx. Okay, so this came from the product rule. Now, the derivative of negative y squared is going to be minus 2y to the first, again, times dy dx, because it was a y term. And don't forget to take the derivative of the right-hand side. Derivative of any constant is 0. Okay? So be careful there. Go back and rewind if you need to. Okay? And again, now we want to get dy dx by itself. So I'm going to leave these where they are, and I'm going to move these 2 terms to the other side of the equation. So we're going to have 2x dy dx minus 2y dy dx, and I'm going to write this as negative 3x squared minus 2y, and a little factoring and division, and we'll be there. Okay, and it looks like, end of the day, dy dx here, negative 3x squared minus 2y over 2x minus 2y. And again, that's the general form of the derivative for this particular curve that we started with. And if we wanted actual slopes of line tangents, we can now start plugging in coordinates for x and y that were along this curve, and we can get the slopes of the tangent lines if we wanted. Okay, let's do another one. Similar to the last, we have 4x squared minus 3xy plus y cubed is 16. Again, we're going to find dy dx. From left to right, derivative of 4x squared is just 8x. Okay, now again we have the product rule. And the thing to notice is that we have a negative out front. Okay, so there's a couple ways to go through this. I mean, I can keep the negative alone, and then I kind of think of this as my product here, the 3xy. So I'm going to do my product rule in a parenthesis or bracket. The derivative of 3x is 3 times the y, plus keep the 3x times the derivative of y, and there's our product. Okay. Derivative of y cubed, 3y squared, again dy dx, and the derivative of our constant is 0. Now, I'm going to distribute the negative through. So we're going to end up with 8x minus 3y minus 3x dy dx. Okay, now typically when I go through these, I kind of am in the habit of going from there to there. I don't really do the parentheses much, so to go from one line to the third line there, basically here's the way I look at it. Okay, I think of this as negative 3x times y. So when I take the derivative of negative 3x, I get negative 3 times the y, keep the negative 3x times dy dx. Okay, so whichever, if you prefer the method I used first, just to help be careful, go for that. But whatever you do, just watch out, okay? Again, I'm going to keep the dy stuff on this side of the equation. And I'm going to bring the non-dy dx stuff over here and factor divide. And there we have it. Okay, so again, watch those product rules, x times y's, okay? Okay, let's take a look at a trig one here. We've got cosine of y equal to the sine of x, and again, we're going to find dy dx. So from left to right, well, derivative of cosine is negative sine of y, and because it was a y term, multiply by dy dx. This derivative of sine x is just cosine x, and because it was an x term, we just leave it at that. And so actually pretty easy to get dy by itself here. Dy dx is going to be cos x over negative sine y. And that's all you can do with that. That does not become a cotangent because the angles are not the same inside of those trig functions. So that is what it is, okay? Another one, we have the natural log of the quantity x times y equals e to the y. So we do have a chain. We have an outer function. We have more than a plain x inside of that log function. So we're going to have a chain. And we got a product x times y. Okay? So for the chain rule, we're going to work from the outside in. The outer function is ln. Okay? We didn't see much of these in that lesson, but here's how it works. The derivative of ln is 1 over. So I'm going to get not 1 over x, but 1 over whatever is inside there. That's me leaving the inner function alone. Now times the derivative of the inner function, and that's what's going to require the product rule. Derivative of x is 1 times the y, plus I will keep the x times the derivative of y, dy dx. And there is the whole left side of the equation. Moving on to the right side, the derivative of e to the y is, of course, e to the y itself, but because it was a y term, multiply by dy dx. Okay? And so we do have dy dx's on both sides of the equation. We'll have to clean that up a little bit. Here goes. I'm going to go ahead and distribute. And let's see, y over xy is 1 over x over xy is 1 over y times dy dx. And just to make life a little simpler, I'm going to move that to that side. Doesn't always have to go to the left. It can go on whatever side, those dy dx's. And now I can factor and divide. And it looks like dy dx is going to be 1 over x over e to the y minus 1 over y. You can leave it like that. If this was multiple choice, realize we have a complex fraction, little fractions within a bigger fraction. To clean that up, you typically multiply on top and bottom by the least common denominator, which in this case is x times y. And so in doing that, in the numerator, I'm just going to have a y. Down below, I'm going to have xy e to the y minus x. And that just looks a little nicer, arguably, than what we started with. Okay, but again, a little tricky. Take your time with these. Watch them again if you need to, okay? All right, here now we're going to actually find a numeric answer, find the slope of the line tangent to this curve at the point 1, 2. Okay, so here we're going to end up with a number, like I said, and basically the idea is this. Look, take the derivative, then we can sub in 1 for x and 2 for y. Okay, realizing we have y's kind of buried in here, we know we're going to do implicit differentiation, so left to right. Derivative is 2. Now I've got the product rule. So the derivative of negative 5x squared is negative 10x times the y. I will keep the negative 5x squared times derivative of y. Okay, derivative of 3y would be 3 dy dx, and derivative of any constant, again, is 0. Okay, so at this point, we have a couple of ways we can go. We can get dy dx by itself, like we have been, move everything over, factor, divide. But the nice thing about taking a derivative at a point is that you don't really need to go through all that trouble to get dy dx by itself. You can plug the values in as soon as you take the derivative here. So that's what I'm going to do. I'm going to plug 1 in for x and 2 in for y wherever I see them. Leave the dy dx's alone. That's what we're getting by itself. All right, so what do we got? 2 minus 20 is negative 18. This is going to be minus 5 dy dx plus 3 dy dx. Negative 5 plus 3 gives us negative 2 dy dx. Okay, and now I'll move one thing to the other side, and I'll divide. And it looks like we have a slope of negative 9. Okay, provided my arithmetic is correct. Okay, but again, you can take the derivative. As soon as you take the derivative, you can plug in x and y values. Okay. Okay, sometimes you'll be asked about finding the slope of the line normal to a curve. Normal is perpendicular to a tangent line, right? So the slopes are negative reciprocals of one another. So if I said the slope of some tangent was 3 over 4, then the slope of the normal, which is perpendicular, would be negative 4/3. Okay? So in this next example, find the slope of the line normal to 2x minus 5y squared over 4y cubed minus x squared equals negative x at the point 1, 1. Nice, we have that coordinate to work with. That should make the arithmetic fairly simple. What's not so nice is that we've got y's buried, which is implicit, and it looks like we have a quotient here. Okay, I don't know about you, but I don't really want to do quotient rule with implicit differentiation. So the point of this example is kind of trying to help show you, other ways around things. Let's try to find the easiest way. I'm going to get around the quotient rule by simply multiplying that denominator to the other side. And I basically did what? I traded the quotient rule now for a product rule. And I can clean this up even a little bit more by distributing. So one thing about calculus is, it takes a little bit of experience and messing around to really kind of try to find the easiest way through problems. Okay, but that's what this practice is all about. So I've done this. Now, look, I've still got a little bit of a product on the negative 4xy cubed, but that's a heck of a lot nicer than that quotient I started with. So I'm going to go ahead and start taking the derivative from left to right. So derivative of 2x, derivative of 5y squared, 10y dy dx. Okay, negative 4x times y cubed. The derivative of negative 4x is negative 4 times the y cubed. Keep the minus 4x, and the derivative of y cubed is going to be what? 3y squared times dy dx. And the derivative of x cubed is just 3x squared. Okay, I'm going to clean this up just a little bit, and then I'll worry about subbing in some values here. Basically, what do we got right here? This is going to be a negative 12xy squared. And again, I'm plugging in the 0.11. I'm going to go ahead and do that now. So wherever I have a y or an x, I'm plugging in a 1. All right, so that shouldn't be too bad. Take a moment to do that. And now I'm going to combine like terms. Basically, I'm going to bring, let's see, I'm going to add the 12 dy's to both sides. Let's see, negative 4 plus 3 is negative 1. So subtract and divide. Okay, so this is the slope of the tangent line. So the slope normal, which again is perpendicular, is positive 2/3 here. Okay? And one more example. Find the equations of the lines tangent and normal to the circle x squared plus y squared equals 100 at the point 4, 6. Okay? So what do we got? Circle centered at the origin, radius of 10. We got the point 46. So the tangent line, by the looks of it, is going to have some negative slope, and the normal line, which is perpendicular, should have some positive slope, I'm guessing. Okay? That's the gist of what's going on. We're finding the slopes of those blue and green lines there, okay? So again, implicit differentiation, because there's a y mixed in. So I'm going to go 2x, 2y to the first, dy dx equals 0. And let's see, 2y is equal to negative 2x, so dividing by 2y on both sides, dy, when simplified, is just negative x over y. So the slope at any point is negative x over y. So tangent, we're going to evaluate dy dx at the point 4, 6, and that's just kind of the notation. We're evaluating dy dx. There's a little bar with the coordinate at the bottom, and we're going to plug in 4 and 6. So what do we get? Negative 4 over 6, or negative 2/3. Okay, that's the slope. That should be the blue line. That's the negative slope. And I'll make the normal one blue. That should be positive. So for normal, positive 3/2, right? Just take the negative reciprocal. And that is implicit differentiation, okay? So take your time, reach out to me if you have questions, and more.